Hello, everyone. Welcome to the ILTA Physics Problem Solving Lecture. Today, we're going to study apparent weight in circular motion. Apparent weight isn't your actual weight. It's the weight you feel with your body when you're in motion. Previously, we studied apparent weight in linear motion, like the weight you feel when riding an elevator up or down. Today's topic is also about apparent weight, but specifically in the context of circular motion. The most typical problem involving apparent weight in circular motion is the roller coaster problem, as shown in the diagram below. A common question type is calculating the weight you feel when a roller coaster is at the very top and at the very bottom of a loop. Let me explain one thing in advance. When you ride a roller coaster, you feel heavier than your actual weight at the very bottom. It's a pretty strange feeling, right? Now, let's briefly summarize the basic concepts for calculating apparent weight in circular motion. Most of the circular motion problems we deal with are roller coaster types. As I mentioned, apparent weight is not your actual weight, but the weight we feel. So first, we need to define what force acts as this apparent weight. Generally, the representative apparent weight we feel is the normal force. Just like in the elevator case for linear motion, the normal force acts as the apparent weight here as well. In roller coaster motion, this normal force is the force the seat exerts pushing up on the passenger while they are sitting. For convenience, we will call this normal force, the seat pushing the passenger, the apparent weight. To solve apparent weight problems in circular motion, you must accurately understand the following concepts. First, for an object to maintain circular motion, a centripetal force pulling toward the center of the circle is always required. This is because the centripetal force creates the centripetal acceleration that keeps the object moving in a circle. Remember, we always need centripetal force for circular motion. However, if you draw a free body diagram of an object in circular motion, there are three forces involved. The actual weight acting vertically downward, the centripetal force pointing toward the center, and the normal force, the apparent weight, from the seat. Let's think about the direction of this normal force. No matter where you are in the circular path, the normal force from the seat will also point toward the center of the circle. Since the passenger's actual weight doesn't change, and a constant centripetal force is required for steady circular motion, the normal force, our apparent weight, must change depending on the roller coaster's position to maintain that constant centripetal force. In other words, the apparent weight varies by location to keep the centripetal force constant for the circular motion. If you understand this fact clearly, you can easily set up and solve any roller coaster problem. Now let's look at the diagram and explain the quantitative physical relationships. Let's imagine the roller coaster starts from the left and moves in a counterclockwise circular motion. Here, we will first define the positive direction using a coordinate system. We'll consider the positive y-axis, or the upward direction, as the positive direction of motion. First, let's look at the case where the roller coaster is passing through the bottom. Let's draw a free body diagram of all the forces acting at the bottom. Gravity pulling the passenger down, the weight points downward. The centripetal force for circular motion points toward the center, which is upward. Finally, the normal force from the seat points upward when the coaster is at the very bottom. Let's look at the relationship between these three forces. Remember that we need centripetal force for circular motion, and that centripetal force must be the result of the normal force, called apparent weight, and the gravitational force, which is called weight. Taking the directions into account, the equation is centripetal force equals apparent weight minus weight. Please keep in mind that since weight points downward in our coordinate system, it will have a minus sign. If we solve this for apparent weight, it is calculated as the sum of the centripetal force and the actual weight. Here, centripetal force is the product of mass and centripetal acceleration, and weight is the product of mass and the acceleration due to gravity. So, to summarize, apparent weight equals mass times the sum of centripetal acceleration and gravitational acceleration. Since centripetal acceleration can be expressed as tangential velocity squared divided by the radius, we can rewrite the equation like this. In terms of physical meaning, when the roller coaster is at the bottom, the apparent weight feels heavier than the actual weight by an amount proportional to the centripetal acceleration. The most important thing here is to understand the free body diagram at the bottom and accurately set up the relationship considering the direction of each force. Please pause the video for a moment and try to summarize this yourself. Now let's calculate the apparent weight when the roller coaster is at the very top. It's the exact same method. Let's draw the free body diagram for the top position. Gravity is pulling downward, and the centripetal force also acts toward the center, which is downward. Which way does the normal force point? At the top of the loop, the seat is upside down, so the direction the seat pushes the passenger is also downward. In the diagram, the blue vector represents the apparent weight. Now, let's set up the equation for these three forces. Negative centripetal force, since it's downward, equals negative apparent weight minus the actual weight. Please take a moment to carefully think about how the direction of the force connects with the sign in the equation once again. Solving for apparent weight gives us centripetal force minus weight. Using centripetal acceleration or velocity, it looks like the following equations. The physical meaning at the top is that the apparent weight feels lighter by an amount proportional to the centripetal acceleration. One thing to note is that the calculated result for apparent weight will generally appear as a negative value. Don't forget that this simply means the direction of the apparent weight is downward. Finally, let me explain critical speed in circular motion. This is the same concept as the weightlessness we studied in free fall motion. We said that at the top, the apparent weight feels lighter. The speed at which this apparent weight becomes zero is called the critical speed. This is the speed where you feel like you are floating in the air while on the coaster. You can find this by setting the apparent weight to zero in the previous equation and solving for velocity. In this case, the critical speed is determined by taking the square root of the gravitational acceleration times the radius. In typical problem-solving lectures, I usually keep the theory brief and focus on the final formulas. But I think I explained the theory of apparent weight today in quite a lot of detail. Don't go looking for a separate theory lecture. Just pause here, summarize what you've understood, and then we'll move on to the practice problems. Problem number 24 says a rider on a roller coaster felt 50% heavier than their actual weight when passing the bottom. It asks for the speed of the roller coaster at that point. Visualize the diagram, and let's draw the free body diagram at the bottom. We have weight pointing down, and both centripetal force and the normal force, apparent weight, pointing up. Remember, we need a constant centripetal force for the circular motion. The relationship considering the directions is as follows. Therefore, the apparent weight at the bottom is the sum of the centripetal force and the weight. Since the question asks for velocity, we will use the equation that includes velocity. Note that since the rider feels 50% heavier, we substitute 1.5 times mass times gravity for the apparent weight. This value equals the sum of the centripetal force and the weight. The mass m cancels out on both sides. Substituting the remaining values, the speed is calculated to be 12.1 meters per second. If your conceptual understanding is solid, you can use the formula directly. But since problems can be modified, it's always good practice to draw the free body diagram on a coordinate system. Problem number 26 involves a smaller roller coaster where the rider feels 50% lighter at the top. We need to find the speed. Again, visualize the diagram and draw the free body diagram at the top. When the coaster is at the top, the centripetal force, weight, and normal force, apparent weight, all point downward. We need a constant centripetal force. Setting this up with the directions gives us the following equation. Again, we use the version with velocity and plug in the given values. Since the rider feels 50% lighter, the apparent weight is 0.5 times mass times gravity. This value equals the centripetal force minus the actual weight. Calculating this, we find the speed at the top is 8.57 meters per second. This is a very typical type of apparent weight problem. Problem number 28 is about the apparent weight felt on a Ferris wheel. The difference from a roller coaster is that on a Ferris wheel, the seat always faces upward, even at the top. So you shouldn't just memorize and use the coaster formula. You need to set up a new equation for the top position. Let's look at the apparent weight at the top of a Ferris wheel step by step. If you can draw the free body diagram on the right correctly, this problem is easy. At the top, weight is downward, and the centripetal force is also downward toward the center. However, the direction of the normal force, the apparent weight, is upward in this case because the seat stays upright even at the top. We need centripetal force to maintain circular motion. If we write an equation for the centripetal force while considering the direction and sign of each of these three forces, we get the following. Make sure you understand the sign of each force based on its direction. Solving for apparent weight gives us the following expression. This is the relationship for apparent weight at the top of a Ferris wheel. Now that we know the principle, let's solve with the given conditions. First, the radius is 40 feet, which is 12.19 meters. The speed is given as 1 revolution every 24 seconds. This means the period is 24 seconds. Speed is the distance, the circumference, divided by the period of 24 seconds. Calculating this, the speed is 3.19 meters per second. It's convenient to calculate the centripetal acceleration first. Velocity squared divided by the radius gives a centripetal acceleration of 0.835 meters per second squared. First, at the bottom. Just like the roller coaster, apparent weight is the sum of centripetal force and weight. Multiplying the mass by the sum of centripetal and gravitational acceleration gives 744 newtons. Next, at the top of the Ferris wheel, as we saw earlier, apparent weight is the weight minus the centripetal force. Plugging in the values gives 628 newtons. The important thing to notice here is that for a Ferris wheel, the apparent weight at the top has a positive value. This means that because the seat always faces up, the normal force also points up. Apparent weight in circular motion is best understood through roller coaster problems. Please practice the theory and the explanations from today's problem-solving session. That's it for today. Great job, everyone. You worked hard for a long time today. See you next time.